Hello everybody. Okay, so in this video we are looking at the sample distributions and the central limit theorem, right? So the sample mean distribution. So if we're interested in let's say the height of all 16-year-olds in Ireland, right? The information we require is generally the mean height of population and a measure of spread, right? Such as the standard deviation of population. But in such a large population, it's actually quite hard to actually get the data I need or calculate what the actual mean is, right? So what we need to do is we need to take something called a sample. And what is a sample, right? Well, all these red dots say represent my population, and these little circles here represent samples I took of the same size. Now, if I take the mean, right, of each of these samples here, right? And I keep on doing that. And if I plot out all the means I get, right, my means will be normally distributed. So if I get the means of loads of different samples and plot them out, that will be normally distributed. So if we take lots of random samples of a given size population and find the mean of each sample, then to plot the distribution of these sample means we find the distribution is symmetric. This forms the basis of the central limit theorem. So what is the central limit theorem? So the central limit theorem states that if we have a population with mean, mu, and standard deviation sigma, and we take sufficiently large random samples from the population with replacements, then the distribution of the sample means will be approximately normally distributed. So there are two conditions that must be met, right? And the first condition must be that we take sample means from groups greater than 30, right? And then the other thing would be the distribution of any sample, so there must be more than 30. So if we look here, right? Here's some normal distributions here. Normal distribution is the so these will be my parents' distributions. So this one's normal distributed, this one's skewed, this one's uniform, this one's irregular, right? And here's if I took random samples from each, and if I increased the size of my samples. So it's 3, okay, 5, yeah, getting more and more normal. Okay, now if I take sample means of 10, yeah, now 20. Now like they're looking more and more like a normal distribution. So in general, we require it to be greater than 30. When it gets less than 30, then we have to be doing things called like t-scores and stuff, but that is college stuff, right? The properties of the sample mean distribution. If the population is normally distributed, the sample normally distribution, the sample means is normally distributed as well. So if the parent distribution is already normally distributed, then the sample means will automatically be distributed. I don't need to worry about taking samples of 30 people, of groups of size 30, right? The mean of the sample distribution is equal to the true population mean, right? So if I take the mean of all my means, that should be equal to my actual mean of the population. The standard deviation of the sample means, also known as the standard error, is equal to this. The standard deviation over square root n, right? And then to convert z to x units into z scores, we use the following. So it is the mean, the sample mean minus the population mean all over standard deviation divided by square root n, where n is my sample size. So I have two different z scores here. So if we are reading a question and it says, we are using, we're getting the sample mean and blah, 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 we have to use this z score here. So let's have a look at one here. So women's height in Ireland are normally distributed. When a mean given by mu is equal to 164.4 centimeters and a standard deviation of 6.25 centimeters. If a woman is selected at random, find the probability that her height is less than 1.67. So we're not dealing with my sample mean distribution here. We're not talking about means or sample means or anything. We're just asked here, what's the probability that a woman is less than 167 centimeters? So we're just doing our normal one here. So minus thing over standard deviation, so minus 164.4 all over 6.25. That would be equal to the probability that Z is less than 0.416. If you look that up in our tables, we'll roughly get the probability that Z is less than 0.42, which is roughly equal to 0.668. So a woman being less than that height, 66.28. But now look here. A simple random sample of 25 women is selected. Find the probability that the mean height of the sample is less than 167 centimeters. So that the mean height of the sample is less than 167. The probability that my sample mean is less than 167. So standardize it, subtract the population mean, all over standard deviation over square root of my sample size. So my mean was 164.4 all over my standard deviation, which is 6.25, all over the square root of my sample mean, or my sample size. My sample size is 25, so square root of 25. So that would be equal to now 167 minus 164.4 over 6.25 over square root of 25 is equal to the probability that Z is less than 2.08. And now I can just look this up in my tables. If I look this up in my tables, I get 0.9812. So there's basically a 98% chance, right, that the sample mean is less than 107 centimeters. Explain why we're able to use the central limit theorem in part 2, even though the sample size does not exceed 30, because the parent distribution is normally distributed. And what do I mean by the parent distribution? If you read the top of the question, the women's heights in Ireland are normally distributed. So the parent distribution is already normally distributed. That's why we don't have to worry about sample size being greater than 30. Right, okay, let's look at this exam question. It's from 2018. We're just going to do part A. So, Acme Confectionery Company makes chocolates, bars, and cakes. Acme Confectionery has launched a new bar called Chocolate Crunch. The weights of these new bars are normally distributed, right, with a mean of 4.64 and a standard deviation of 0.12 grams. A sample of 10 bars is selected at random, and the mean weight of the sample is calculated. So I see sample mean, right? So I'm going to use my Z scores here. Find the probability that the mean weight of the sample is between 4.6 and 4.7. So the sample mean in 4.6 and 4.7. So standardize the over square root n. So that would be minus 4.64 all over 0.12 all over square root of 10. So I get now the probability that minus 5, 1.58. So I now need to find the probability the Z score between minus 1.05 and 1.58. Sketch it out. Right, so minus 1.05 would be here, 1.58 would be here. I need to calculate this. This will be equal to Z less than 1.58 minus probably that Z is less than minus 1.05. So this here for my tables will be 0.9429. And I'm subtracting here 1 minus the probability that Z is less than 1.05. 0.9429 minus 1 minus 0.8531. 0.9429 minus 0.1469, which is equal to 0.79. Now be it there. So there's roughly 79.6% chance that the mean weight of my sample, these chocolate bars, will be between 4.6 grams and 4.7 grams. Right. Okay. I hope this video, guys. Right. And I'll catch you guys there. Bye.